So here's our practice. The first example, we have an object that is being pulled and it's resting. So despite the force of pull, it's not moving, which reminds us of Newton's first law, which tells us that an object at rest stays at rest if forces are balanced. If net force equals 0, then the object is going to stay at rest. So we have our force of gravity, we got a matching normal force, so they balance each other out. And then if I have a pull of 20, then I will have a matching force of static friction, which is also going to be 20 newtons. So force of friction, if we have rest, then we have force of pull equal force of friction static, and it will be equal to 20 newtons. Then the second, what if the mu static between the box and the floor is 0.25? What kind of force do I need to, the minimum, think about the minimum pull that we need to apply in order for the object to move. In this case, I don't know what my pull is. I just know that mu static is 0.25. So then the maximum force of friction static that is available could be found as mu static times normal force, and it would be 0.25 times 5 times 9.8, because like I already said, force of gravity and normal are equal in this situation. Then this would be going to be 1225 newtons. So it's just a different setting. It's not the same box and the same floor. So if we apply a force of pull greater than 1225, the object is going to be moving, 1226 or something like that. So that's your answer to question number 1. Question number 2, in this case, the object is at constant speed and it's moving. So if I put static friction here and just lazily duplicate this, because it's going to be the same, I need to change this to kinetic. Boom. Because it's constant speed, then force of pull still equals force of friction, in this case kinetic. Then what is the kinetic coefficient? So mu k is the ratio of force of kinetic friction and force normal, according to the formula for force of friction. Remember, force of friction equals mu times normal force. So since we're talking about kinetic friction, we're talking about kinetic coefficient. So we are after the coefficient that is kinetic. If force of pull equals force of friction, then I can use 30. And then normal force should be equal to gravity. So that's going to be 98, because that is going to be 10 times 9.8. So 30 divided by, so it's about 0.3, a little more than 0.3, like 0.31 probably. Yep, 0.31. And mu does not have any units because it's a ratio. Newtons divided by newtons is nothing. Newtons cancel. Example number 3. Example number 3 asks us to figure out whether the box is going to move if we apply 55 Newton force. So there is friction, and see how they sneakily give us 2 mu's. In order for us to figure out if it's going to move or not, we need to find the static friction and compare it to the force of pull. And if force of pull is greater than the static friction, then it's going to move. And if it's not, then it's not going to move. For now, I'm just going to say force of friction static here. That is going to be 15 times 9.8. So we've done it a bunch of times. It's 147 newtons. Force of static friction, take the mu s and times normal force. So it's going to be 0.42 times 147, 61.74, 62 newtons. That is how much force of friction static can get to. And remember, in the lab, as I increased the pull, force of static friction was increasing. So if I apply 55 Newton force, is there enough available friction to stop the object from moving? Yes, there is, because 62 newtons is greater than 55, then no, it's not going to move. And then you stop. You don't need to do anything else. In question 4, which is basically related to question 3, now the same box is being moved with a 65 Newton force. Well, if it's a 65 Newton force, then I know that it's going to break force of friction static. And if it's going to break force of friction static, then it's going to be friction kinetic. And kinetic friction is less than static friction. So I am sure it's going to accelerate. And I now need to find acceleration. To find acceleration, I need to use Newton's second law. So you know net force equals mass times acceleration. So from there, acceleration is net force divided by mass. And that net force is going to be pull minus force of friction. Which friction? Kinetic, because it's going to be moving. Boom. Divided by m. Force of pull being 65. Force kinetic is going to be, instead of 0.42, it's 0.37 for mu kinetic. So 0.37 times, it's the same box for 147 for gravity, divided by 15.71 meters per second squared. That's our acceleration. Question 3 and 4 are based on each other. In question 3, it wasn't moving because our pull was less than friction static. But in example 4, that same box was pulled with a 65 Newton force, which was greater than the maximum static, which was only 62. So in that case, we had to replace the static friction with kinetic friction, because once the object starts moving, static friction is no more, and we have kinetic friction to calculate. Next, we have a hockey gear duffel bag. Sorry, this is misspelled. Duffel. It's pulled to the right with 175 Newton force. The acceleration is 2.2. What is the mu k between the bag and the floor? All right, so I'm just going to lazily copy this right here because I can, and because it's the same situation. The only difference is now the force of gravity is 35 times 9.8. 343 newtons. Going back to Newton's second law, net force equals mass times acceleration. Net force is still the difference of two forces, which is force of pull and force of kinetic friction. Force of pull is 175. Force of kinetic friction, and then it should be equal to mass times acceleration, mass being 35, acceleration being 2.2. Force of kinetic friction is going to be the difference of 175 minus, what's 35 times 2? That's like 77. So that's going to be 98. Then mu kinetic is going to be the ratio of 98, which is force of friction, to normal force, which is 343, just like gravity. 98 divided by 343 gets us 0.29. No units because it's just a ratio. So that's our coefficient of kinetic friction. And that concludes this practice sheet. I hope this was helpful. I'll see you in class.